section, and that ought to do her for today. Does anyone have anything from 4.1 that we'd like to talk about? Yeah. I'd like to caution you guys. I know that we've told you we're not doing homework quizzes here for the rest of the semester. I still really need you to do at least some of the homeworks between this class and next, even if it's just like a handful of questions. In particular, this string of sections we're doing, 4.1, 4.2, 4.3, are really closely related. And I think things will go much smoother if you've had a little bit of practice with one set of ideas before we move to the next set and move to the next set. Kind of these three sections all really closely build on each other. So I know that some of us are probably just like, this is going to be a Thanksgiving break problem. And I understand, like, I'm really sympathetic to that. I have a lot of things that I've designated as Thanksgiving break problems also. Like, I don't want to deal with it right now. But just try to do a little, even if it's just a handful of questions, it makes a big difference. Okay. Chanel?
One of the 4.1, 4.2, and then next class is 4.3, right? When are those problem sets due? Sunday?
I don't know. What's going to be easier for you guys? You want it the Sunday at the start of break or the Sunday at the end of break?
End of break? I would prefer end of break, but... That's
fine. We'll turn it in then. I just didn't know if it's like, you need to make this so I get it done beforehand so I can concentrate on other stuff afterwards. And it like forces me to get it done and I can move on to other stuff versus procrastinating. But whatever. I don't care. Tell you what. I'm not looking at anything until I get back from break. So whenever it gets done, you can put it in there and I'll see it when I get back from break, and I'm not going to look at anything in the interim.
So we can turn it in before, like we can turn it at the end of break?
Sure. Yeah, I won't look at any homeworks until after we come back from Thanksgiving. How's that sound? Okay. Nolan.
I do remember I talked about one of the differentials required
Oh yeah, we did one of those. Which one did? Oh, you want to do that one? We can do that one. It was 57. Yeah, let's do it. This was a fun one. So the directions on this set of problems were to find the absolute maximum and minimum values of f on the given interval. Now, we're going to treat this as a no calculator problem, because if it was a calculator problem, it's like you graph it and find them, right? Like pretty easy. So let's first start by looking at the domain of f. What's the domain for f? If f is 2 cosine t plus sine 2t. All real numbers.
Oh, yeah, the range.
Yeah, the range of those. Yeah, that's what you did. Yep. And it would be 3, I think, because you'd have 2 cosine and then plus 1 from sine, right? So it could be -3 to 3 for the range. But yeah, but really in our case, the domain that we're interested in is specified to be 0 to pi over 2 in the problem, right? Then let's do the derivative. What's the derivative of 2 cosine t? Excellent. Say it loud and proud so we can all be impressed. And then the derivative of sine 2t. 2 cos 2t. Fantastic. What's the domain for f prime? Great. Again, since it's still two sines and cosines just added together. So rather than writing all real numbers and then crossing off and writing it's still the same domain, right? So we have no critical values from the derivative being undefined, right? All of my critical values are going to come from solving that derivative equal to 0. So we're going to solve this equation equal to 0. How are we going to do this? Can be done all algebraically, no calculator required.
Can't you factor out the 2 first?
Sure, yeah, let's do that. I'm just going to divide the 2 to both sides, and that'll get the 2 out of there. Sure, that's a good idea. No. Yeah, so the big issue right now is I have sine 1t and cosine 2t. I want to get that to be the same sine or cosine of just t's. Everybody okay with that? So there's a double angle theorem for cosine. In fact, there's 3 double angle identities for cosine 2t. The question is, which one do we want? Do you remember what any of the 3 are? Oh, that's okay. Let's look again. So cosine squared minus sine squared, that's the one I always remember. And then I usually derive the other 2 as just using like cosine as 1 minus sine squared, or sine squared as 1 minus cosine squared. But the one we're going to want is 1 minus 2 sine squared. Why do I want that one? Yeah, because the other trig function in my problem is a sine. Good. And let's see, I'll divide both sides by a negative and then kind of rewrite this in a more sensible order. How should I solve that now? Two sine squared t. Yeah.
You turn the minus 1 into sine squared plus cosine.
You could. I wouldn't want to, though. What? Yeah, it's a quadratic, right? You can treat it like, you can use the quadratic formula, except when you use the quadratic formula, instead of getting x equals, what would we have this time? Not t equals. We have sine t equals, right? Or what else could we use to solve a quadratic? Factoring. That's what I'm going to do, because I noticed that this thing is, if it's factorable, it should be pretty easy because the coefficients are 2, 1, and 1, or negative 1. So if it's factorable, it's going to look like that. I just have to decide where the plus and minus should go, right? One of them needs to be a plus 1, the other needs to be a minus 1. What should go in the first parentheses? 2 sine t should be plus 1 or minus 1?
Plus. Right.
Minus. Because I need 2 sine t minus 1 sine t to give me sine t. So I just kind of did that by inspection. I didn't do like the long factoring process because it was like, there's really just 2 options. It's just One has to be a plus and one has to be a minus. If you weren't steady on your factoring, could you have done the quadratic formula like Katie and Giselle suggested? Absolutely. Is it any faster to do it that way? Probably not. It's probably about the same. Now that we have this, we can apply the zero product property and set each of these factors equal to 0. So I'd have sine t equals 1/2, and then sine t is equal to -1. So we'll do sine inverse of both sides. Where on the unit circle is sine equal to 1/2? Again, the AP people expect you to know this without a unit circle. Sine of 45 is root 2 over 2. $30, but we're in AP, so this is, we want it in radians. Yep. Is that the only place on the unit circle? No. Should it be in quadrant 1 or 2 or 3 or 4?
5 pi over 6.
5 pi over 6 is correct. Yes. Should also be in quadrant 2, and the reference angle should be the same. If we do the same thing over here, sine inverse of -1. Where is sine equal to -1 on the unit circle? This one should be easy.
3 pi over 6.
Excellent. Now, let's look here because remember, what is our domain that we're working under?
0 to
So that one's out of here, that one's out of here. I just have one option. So far, so good? So to check for my absolute maximum and my absolute minimum, I need to check the boundaries of my interval and my critical values, right? Everybody okay with that? So we have 2 cosine of 0 plus sine 2 times 0. What is cosine of 0?
1.
That's correct. And sine of 0?
0.
So the value of f of 0 is 2. What is cosine of pi over 6? Should helpful to remember that sine of pi over 6 was 1/2. It's not 1/2. What's the coordinate that goes with 1/2? Not root 2 over 2. Root 3 over 2. And then sine of pi over 3 is root 3 over 2. Remember that sine and cosine of complementary angles are equal, right? Like sine of 30 should equal cosine of 60, right? So if I do that, let's see, what do I got? I have 3 root 3 over 2. Is that bigger than 2 or smaller than 2? So the way I'm going to think about it, 3 over 2 is about 1.5. Root 3 is about 1.7. 1.5 times 1.7 is bigger than 2. Everybody agree? Think about like 1.5 times 1.7 is 1.7 plus like 0.8, right? One of them plus a half of them. All right, next one. 2 cosine of pi over 2 plus sine 2 times pi over 2. Cosine of pi over 2 is, these quadrantals you guys should be spitting out. Nope. 0, very good. X coordinate 0 there, right? And sine of pi. Good. So my maximum value is 3 root 3 over 2. And my minimum value is 0. And 2 is nothing. How do I know that those were the max and mins? Just the biggest and smallest. Absolutely right. Now, would Mr. Kulik give you something that's irritating to do on a test? No. Don't have a good reputation anymore, do I? No. There's too much trig on this for me to ask you to do on a test, to be completely honest with you. Maybe if I gave you calculator, I'd be fine with doing this, or you can just do the sine inverse on your calculator and plug the stuff back in with your calculator, like much less irritating of a question. But with a no calculator, in a time like quit test setting where I just ran too long on the last one, I wouldn't give you something that's like this annoyingly time consuming, because you'd have to like really go back and think about all these trig things.
On the AP test, would it be like this, kind of? Like, would they put that much trig?
I doubt it. In one question to have that much. Yeah, the quadrantals you really have to have. Like being able to do cosine of pi and cosine of 0 and sine, like that stuff should be like quick and automatic at minimum. And again, I don't memorize the unit circle, but I know it. And the way I know it is, like this is the x and y coordinates are cosine comma sine, right? So here, this is big and this is small. So like 1/2 and root 3 over 2. And that first angle is 30 degrees, and I just kind of count around where it's like cosine of 1/2. Is that where the terminal side is close to the x-axis or far from the x-axis? It's, except I wrote that in the wrong way. That should be this way. Mr. Kulik. Because the x here is long and the y is short. And that's all I'm thinking about. I'm just thinking about long and shorts because I know the 3 coordinates are going to be 1/2, root 2 over 2, and root 3 over 2. Smallest is 1/2, middle is root 2 over 2, biggest is root 3 over 2. That's all I'm thinking about. It's just like short side, long side, short side, long side. And then I don't really have to memorize anything. I can just picture where the angle is in my head and go, okay, short side, long side. I don't know if that helps at all. From the glazed look over most of us, it doesn't seem like it really did, but I'll move on anyways. Who else has questions from 4.1 that we'd like to talk about? This was a doozy, right? Like that was involved. There's a lot to do, a lot of trig stuff to remember. You guys that did 4.1 stuff, were they all this bad? No, they was largely pretty straightforward. The calculus was pretty easy. The algebra was pretty easy. Understanding how to mix them together was maybe the hard part. But once you've done a couple, it really kind of becomes a little bit more straightforward. It's like, okay, it's just kind of the same procedure every time. Does anyone else want to ask anything about 4.1 for today? I'm going to pick a problem from the 3.9 AP questions that I asked you guys to do. And we're going to do 14 today from the multiple choice.
That one was hard.
Yeah, this one, I think, was maybe the hardest of the multiple choice questions. We're just going to kind of walk through it here together.
Wait, Mr. Cohen, after you do 14, can you take up the 1 of the
Not right this second, but eventually. Sure, we can do it. I'm just cognizant about running out of time to do
I'm
4-2
sorry.
today. That's okay. No, it's fine. It's not a big deal. That's why I said maybe not right now.
Okay.
So this reads, a model car travels around a circular track with a radius of 5 feet. Let Z denote the distance between the model car and a fixed point that is 20 feet to the left of the center of the circular track. So to me, that looks like that segment there is our Z, right? Where O is our fixed point. The diagram above indicates the fixed point at the origin, the center of the circular track at the point 20, 0, and the position of the car at point XY. Z is the length of the segment from the origin to point XY. If X and Y are functions of time in seconds, what is the rate of change of Z when X is equal to 23 and Y is equal to 4? So it's asking us for the value of dz dt when X is 23 and Y is 4. And we're told that dx dt is equal to 2. Everybody okay with the explanation that we have and the comments about the picture? So what equation do we have that relates or that involves Z? What is Z again? The distance between 2 points. Do you guys know of an equation that describes the distance between 2 points? The distance formula is exactly what I would want to use here. So remember, the distance formula is the square root of like x1 minus x2 squared plus y1 minus y2 squared. Everybody's okay there? Let's say our point xy is like our x1, y1. And let's say the origin there at O is like our x2, y2. Everybody's good? So z is then the square root of x squared plus y squared. Everybody good so far? So if I take the derivative right now, I'm going to get dz dt. When I have to differentiate the x squared, I'm going to get a dx dt. And when I have to differentiate the y squared, I'm going to get a dy dt. That's a problem though, right? We don't know anything about dy dt. We don't have a way to get dy dt. So my first order of business here is going to figure out a way to eliminate the y squared from this equation. Are we okay with the reasoning as to how I came to that conclusion? Okay. The piece of information that I've been given for this problem that I have not yet used is the equation for a circle. So let's see what we can get from that. So here's our circle, right? So let's write our equation. What's the center of our circle? The x-coordinate? 20. And what's the y-coordinate? 0. Good. And what's the radius? 5. How'd you know that? It's given to us in the problem. We read it at the very beginning, but I didn't write anything down about it. Okay, so let's clean that up maybe just a little bit. And hey, look! This is another equation that has a y squared in it, right? So let's get that y squared by itself. And now we'll substitute into our equation for z. Is everybody okay with what I did there? I've effectively eliminated the y's now. At this point, we have a couple of options. We could simplify the stuff inside the square root, FOIL out the x minus 20 squared and do all that mumbo jumbo, or we can just differentiate it as is. That's probably the route that I would go because the algebra looks worse than the derivative at this point. But it doesn't really matter. You could go either route. Okay, to differentiate the square root of x squared plus 25 minus x minus 20 squared, what do I have to do? Chain rule. Great. What's the derivative of the outside?
1/2 x.
Yeah, 1/2 insides to the negative 1/2, and then times the derivative of the insides, right? So far, so good? Okay, all this stuff just kind of stays. And then the derivative of x squared with respect to time is? Excellent. Forgot to write the dz dt. And the derivative of 25 is? And then the derivative of negative x minus 20 squared.
2x.
It's a chain rule. You cannot distribute exponents. And we do need to remember a dx dt there again, right? When we do the derivative of the inside of that little tiny chain rule there. Guess what? That's what we need, right? We have an equation for dz dt in terms of just x and dx dt. And I think, let me look real quick. What does that come out to? 40 over root 545. I'd point out to you that this was a calculator active question, so that a decimal would have been appropriate here also. So if we go back and we look at our possible answers, notice that in the possible answers, they give you the exact value and the decimal. Which one should we pick, though, B or C? B is correct. Why B and not C? What's that, Casey? Is what negative? No, the answer that we got was positive, but what is that telling us then? It's telling us that Z is increasing, right? How would that be possible? That point's got to be moving in that direction. So that line, Z, is getting longer each time. What does that mean? It means that the car is moving away from the observer, right? Because the Z is getting further each time. If our derivative was negative, then it would tell us that Z must be getting shorter, so the car must be going towards the observer. Does that feel okay? I don't know that I can unlock them after they've been expired, but I did put the questions inside of the content library, and so they're there also. Is that okay? Okay. And I'm not going to end up like doing anything with them. I just wanted you to have some instant feedback, so that's why I made the thing as a MyAP thing. I'm going to put answer key up in here, I don't know, soon for these questions also. Does that feel okay? And if I can, I'm not sure how to unlock. That's okay.
Yeah.
It'll be okay. All right. As long as we're okay. There's probably a way to do it, but it'll take me 15 minutes to figure it out. And I just feel like I got 15 more productive minutes to eat in my life. All right. Let's stop here. We'll continue to do 3-9 examples because I know that this is not trivial. This is starting to feel more familiar as we go through and do these. Okay? Keep in mind that on an open homework test, you'll be able to bring examples with you. Okay? All right. So let's look at 4.2, which is a little bitty short guy, although it has some really important ideas. So the first idea we're going to start with is called Rolle's theorem. This one, even though it has a name, Rolle's theorem isn't one that has a lot of application. Mostly it's here because we would use it to prove the mean value theorem, which we're going to talk about in just a moment. But let's talk about like what Rolle's theorem is saying. So this says let f be a function that satisfies the following 3 hypotheses. F is continuous on some closed interval from a to b. F is differentiable on the open interval from a to b. F of a equals f of b. If those 3 things hold, then there has to be some number, we'll call that number c, in between a and b such that the derivative evaluated at c is equal to 0. So let's think about what that's really saying. So let's say we have some function whose endpoints are at the same height. That's what f of a equals f of b means. And it has to be continuous, so it has to be connected. And I can't have any sharp corners on it because it has to be differentiable. Well, I could just draw a straight line, right? Well, that would mean then that every c in between a and b has a derivative of 0. So that certainly fits the criteria. We don't have just one c, we have infinitely many c's. That's okay. So again, I'll do the same thing, and maybe I'll have it go like that this time. Oh, look, I have to hit a maximum because at some point I have to turn. I go up, and I have to turn to go back down to get to the starting height. That's going to create a maximum. Well, we know the derivative is 0 at a maximum or minimum. And I could do like, okay, well, I could do that lots of times, right? So I could have finitely many maximum or minimum, or places, finitely many maxima or minima, which gives me finitely many places where the derivative is 0 in between. Or I could go like down and do it, right? And just have minimum But again, like a minimum has a derivative of 0, so no matter how I draw that, I definitely have a place where the derivative is 0 because I'm not allowed any breaks and I'm not allowed any sharp corners. So I definitely have a place in there where the derivative is 0 because I have to have either a horizontal line or I have to have some maximum and minimum or minimum in there. At least one. Does that feel okay to you guys? That's all this is saying. Just saying if you got 2 points at the same height and your function is continuous and differentiable, somewhere along the line, the derivative was equal to 0. There had to be a maximum or minimum, or just like you had a flat line. So let's look at this example here. We're going to be asked to prove that the equation x cubed plus 1 or plus x minus 1 equals 0 has exactly one real root. So to do this, we're going to call this guy f of x. We're going to start by just showing that f of x has at least one real root, right? We want to eventually show it has exactly one, but let's show the easy part first, that I know there's at least one. How would I find at least one real root? Giselle, you're saying something. Go ahead.
I was saying like take the derivative.
You don't need a derivative.
Solve for x.
Okay, so the obvious answer could be solve for x, right? What's the problem with trying to solve x cubed plus x minus 1 equal to 0, supposing you had no calculator?
X cubed.
It's a high degree polynomial, right? There's no closed form formula to do that. Not something that is factorable on site, not by me, so certainly not by you guys. So that's a problem, right? We do have a tool from way back in the first test that you could use to do this.
Limit.
It's not a limit. It is the intermediate value theorem. If I can find a y value that's negative and a y value that's positive, I can guarantee that I had a y value that was 0 because f of x is a polynomial, so it's continuous, right? So we know f of x is continuous because it's a polynomial. Give me an x value that makes f of x negative. Okay, I would have used 0, but negative 1 works. Give me a value for an x so that f of x is positive. You really hate me. How about 1? So that's 1 plus 1 minus 1, so that's 1. Everybody agree? So since f of negative 1 is less than or equal to 0, which is less than or equal to f of 1, the intermediate value theorem states there exists some c on the interval from negative 1 to positive 1 such that f of c equals 0. Does that sound familiar? Right? That's like an intermediate value theorem. We've done that a couple of times. So we know we have to have at least one 0. To show that it has to be exactly 1, what we're going to do is do a proof by contradiction. Okay? So the way up the structure for a proof by contradiction, the way this works is you're going to assume that what you want to prove is false and show that if it's false, then it creates some kind of impossibility, some kind of contradiction. Okay? So what we want to prove is that there's exactly one real root. So we're going to assume that there are at least two real roots. And without loss of generality, let's just say exactly two. Everybody okay with that? So let's assume there's some C star where C star is not that C we found before, and f of C is equal to 0. And just for simplicity's sake, let's assume that that C star is bigger than C.
What does C star represent? Sorry.
It's some other 0, right? That's not the one that we just showed exists. All right. So note here that we have the conditions for Rolle's theorem. Is x cubed plus x minus 1 continuous from C to C star? What do you think? You should be able to answer this question. It's yes or no. Yes, why? F of x is a polynomial. What's the domain of a polynomial? All real numbers. So certainly it's continuous from C to C star. Okay? F is differentiable on the interval from A to B. How do we show that Rf, x cubed plus x minus 1, is differentiable? What's the derivative of this polynomial going to be? Another polynomial. What's the domain for that polynomial? All real numbers. That means the derivative exists for all real numbers, correct? Which means that it was differentiable everywhere. For us, that means from C to C star. Everybody agree? And then note that f of C is equal to 0. F of C star is equal to 0. So that fits condition 3, right? Everybody okay with this? So what does that allow us to say? There exists some other C, we'll call it C double star, on that interval from C prime to C, such that f prime of C double star is equal to 0. But what's the derivative of f going to be? Three x squared plus 1, right? What's the range for that function going to be? Not all real numbers. So if I take 3x squared, what can come out of that? Has to be greater than or equal to 0, right? And if I add 1 to that, this has to be always greater than or equal to 1. Did you see what happened? What just happened? Yeah. We're saying that there has to be some C double star where the derivative is 0, but we've just shown that the derivative is always greater than or equal to 1. Guess what that is? That's our contradiction. That's our impossibility, right? Yes. I would not ask you to do something like this on a test. But many of you are going to take 2, 3, 4, 5, 6 college math classes. This will not be the only time you see a proof by contradiction. The farther you go, the more often you're going to see this kind of a proof structure. It is super common to prove something exists, to prove something is unique, to prove like something can happen. These are like really tailor-made structures for proof by contradiction. It's often going to be the simplest way to prove something like that. That's a very general statement. Is you assume like, okay, what if that doesn't happen? And let's look to see if something impossible needs to be the result then. But yes, that paragraph would be our proof. And in fact, I left things out of that paragraph that we just talked about when I verified that we met the conditions for Rolle's theorem. You'd want to spell each of those out by hand or individually that you met those 3 conditions before we said by Rolle's theorem. But I just did that by talking because it felt like it's good enough. But the deeper you go into your mathematics class, the more actual writing and explaining would be your solutions and the less numbers you're going to see. I don't know if that's reassuring or terrifying. Let's look at the mean value theorem next. So this says, let f be a function that satisfies the following hypotheses. So f is continuous on the closed interval from a to b, and f is differentiable on the open interval from a to b. If we meet those 2 conditions, then we know that there's some number c, where the slope of f at c is equal to the average rate of change, or the slope of the secant line from a to b. So this is like, you can think about this as your average rate of change, or a secant, or a slope of a secant line. This would be your instantaneous rate of change, or the slope of a tangent. So let's visualize this, right? Because just the symbols are a little mysterious sometimes. Let's look at an example here. So if I look at this picture here below, the curve in black is our f of x. We have our points a comma f of a and b comma f of b. The blue line between them is our secant line. The slope of that secant, what the mean value theorem is saying is that there must be some other tangent line I can draw to f, where that tangent line is in between a and b, where the slope of that tangent line is the same as the slope of the secant line. The pink, you're fine, go ahead.
Thank you.
The pink line there is our example of a tangent line that has the same slope as that secant line, right? So like this is our c, that x-coordinate. And we can see in our eyes that those 2 slopes have to be the same. Why? The blue line and the pink line have the same slope because they look parallel, right? That's all we're saying. Could this happen more than once? Yeah. Look at our next graph. Again, the black is our f of x. The blue is our secant line. And you notice there's 2 places where I can draw a tangent that's parallel to the secant line. Is everybody okay with that? Let's do an example of finding such a c. Okay? So let's look at this example. Here our f of x is x cubed minus x. Our a is 0 and our b is 2. So first step, let's verify that f is continuous from 0 to 2. Is that true? Yes. Why is that true? How do you know that? It's a polynomial. Everybody's okay with that? F of x is x cubed minus x. The second thing we have to confirm is that f is differentiable from 0 to 2. Is that true? Yes, it is. Why do you know that? Because the derivative of a polynomial is a polynomial, which is domain is all real numbers. Everybody good with how we confirm the first two? Notice I didn't actually do any calculus here. I just took advantage of like some general facts we know about polynomials and the differentiability of polynomials. Okay. So we know then by the mean value theorem that there exists some c on 0 to 2 such that f prime of c equals f of b minus f of a over b minus a. So far, so good. So what's the derivative of f? 3x squared minus 1. What's f of b? I'm sorry, f of 2. 8 minus 2. What's f of 0? 0. Say it loud and proud when you know it. And what's b minus a? 2. So I should be, what I need to do is find the x where 3x squared minus 1 is equal to 3. What do you want to do how do we going to solve that one? You could, but notice there's only an x squared term. So it's even easier than trying to do something like that. What could we do since there's only x squareds? That's what Casey just suggested. Solve for x directly, right? What do you mean by that, Brooke? Mm-hmm. 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 Now, are both of those our answers? No, why not? How do you know there's only one? We saw an example up here where you had two C's. Which one is not in the interval? The negative. Very good. Remember, our interval is from 0 to 2. So we want only the positive. Everybody okay with that? Again, calculus, pretty easy, right? The derivative, super straightforward. Algebra was pretty easy. The solving was pretty straightforward. Knowing what to do and how to do it, that was the hard part, right? This set of problems, or this set of sections that we're going to be looking at, 4.1, 4.2, 4.3, that is the name of the game. The actual mechanics, pretty straightforward. Knowing what to do and when to do and how to do it, that's the tricky part. But once you've done some examples, you start to fall together and you're like, okay, to do this, I need to do this procedure. To do that, I need to do this procedure. And you start building the relationships between these different ideas and it gets simpler, but you got to practice it. Okay? All right, let's do this next example. So it says, suppose that f of 0 is equal to negative 3, and f prime of x is less than or equal to 5 for all values of x. How large can f of 2 possibly be? Do you guys like pictures? I like pictures. So let's say here's 0, -3, and there's 1, and there's 2. Let's assume the biggest possible slope, which is 5. For starting at 0, -3, where would the next point be where x is 1? What could the next point be if x is 1? 1, 2. Very good. How'd you get that, Christian?
5.
Great. So you went over 1 and up 5. Because the biggest possible slope I can have is 5. Okay? Assuming that we had our biggest possible slope of 5, if we're starting at 1, 2, and we want to end when x is equal to 1, what can we get to? 2, 7, right? Again, how'd you do that? I over 1, up 5. So the biggest f of 2 could possibly be 7. Could it be smaller? Sure. I only asked for an upper bound. How large could it possibly be? Everybody okay with that? Really simple idea, but until you've seen an example of it, you read that and you're like, what am I doing with this? But it's just like, that's the biggest possible slope. So do your over and ups as many times as you can with the biggest possible slope. It's as big as you can get. Or if it was reverse and you want to get the smallest you could get, if it was the slope was less than or equal to something, then you just do the same idea. Smallest possible slope as many times as you can. All right. 2 more theorems. In the interest of time, I'm not going to prove either of these two. So the theorem 5 says if f prime of 0 or f prime of x is equal to 0 for all x on an interval from a to b, then f is constant on that interval from a to b. Does that make sense? If every x has a slope of 0, what is that saying to us? Got to be a flat line, right? Everybody agree? Okay. Could it have a jump in it? No, why not? It would not be differentiable at the jump. So the f prime at the jump would not be equal to 0. It would be does not exist, right? Good. And that seems pretty obvious, right? When you think about that for a minute, it's just like all we're talking about is just it has to be a flat line. Horizontal line, flat line. What is flat? Stupid. All right, anyways, next one says if f prime of x equals g prime of x for all x on some interval from a to b, then f minus g is constant on a, b, or in other words, f of x equals g of x plus c, where c is just some constant. So let's think about what this is saying. If f prime of x and g equals g prime of x for all x, it's saying that the tangent line at every point on f of x is parallel to the tangent line at the corresponding point of g of x, right? So if that happens everywhere, those two functions have to basically be the same function, just running parallel to each other or on top of each other. They could be coinciding. So for example, say our f of x is x squared and our g of x is x squared plus 2. Note that f prime of x and g prime of x are the exact same thing, right? But notice that f of x and g of x are just, parallel functions to each other, right? That's all this is saying. I got one more example. Here it says, prove the identity tan inverse of x plus cotangent inverse of x is equal to pi over 2. The idea here is we're going to be using theorem 5. So we're going to imagine our f of x is like the left-hand side of that equation. And we're going to look at the derivative of that. What's the derivative of inverse tangent?
1 over 1 plus x squared.
Good. And the derivative of cotangent inverse?
1 over x minus root x.
Just the opposite of tangents. What do I get when I add those together? 0. So that's met the conditions there, right? So I know this is equal to some constant. So far, so good? Now let's find that constant. How would we do that?
Can you solve for x using the derivative equation you just found?
It's easier than that. If f of x is constant, then regardless of what x I plug in, as long as it's in the domain of f of x, should give me that same constant value, right? Like if f of x is equal to 5, if I plug 2 in, I should get 5. If I plug 10 in, I should get 5. Plug negative 14 in, I should get 5. So all we need to do is plug in a value into f of x, and it should spit out the constant. Now, we have to ask ourselves, one, we want to make sure the value of x that we pick is inside the domain for f of x. Two, we want to make sure that we pick something that's going to be easy to evaluate. So what number would be easy to take both the tan inverse of and cotangent inverse of? Excellent. Why? Easy to square? It's pi over 4. And what's lovely is, what's the relationship between tangent and cotangent? They're reciprocals. Opposite means they have different signs. Reciprocal means flip fraction. So if I want to do cotangent inverse, that's the same thing as taking tangent inverse of the reciprocal of 1. But what's the reciprocal of 1? 1. So they should give you the same thing, right? Does anybody remember what tan inverse of 1 is?
Pi over 4.
Yeah. And cotangent inverse would be the same thing. You add those together, you get pi over 2. There you go. Would have that worked for any value of x as long as it's in the domain? Yes. Where could have you gotten in trouble? Outside of the domain. For example, 0, right? What's tangent tan inverse of 0 is 0, but cotangent inverse of 0 is undefined. Pi over 2 would have created a similar problem. Tangent of pi over 2 is undefined. Cotangent of pi over 2 is 0. But as long as you pick something that's not one of those multiples of 90 degrees, I think you're good. So even if you had gone to your calculator and you did like tan inverse of 0.3 plus 1 over, I just would be, tan inverse of the reciprocal of 0.3, you get, I'm in degree mode, but 90 degrees is the same as pi over 2, right? As in, we're doing degree stuff in trig. So that's that, which is, hopefully you recognize as pi over 2. So it doesn't really even matter what x you're plugging in, as long as it's in the domain. Now, if you have no calculator, you want to be careful about the x you pick, because you want something you can do, tan inverse and cotangent inverse of easily. Other options might have been root 3 or root 3 over 3. Those would have been good ones. Those are either, pi over 6 or 3 pi over 6, respectively, and are still doable by hand. But that wraps up 4.2 on what I wanted to do today. So the big takeaway, the thing you're going to need, is the mean value theorem, and being able to use that effectively, and what can I do with that? Okay, you really need to, this chapter in particular, it's going to be important that you know like the conditions in which you can apply like the extreme value theorem, the mean value theorem, intermediate value theorem, like what do you need to have, and then what do those things allow you to say? Those reek of multiple choice questions, right? I'd like to point out to you that I put up multiple choice questions and free response questions. I didn't include anything from 3.9 in those sections because we already have 3.9 multiple choice and free response questions. So I didn't feel like bombarding you with more of that was going to be worthwhile. As we get a little bit closer, we can do that if you guys need it. Yes, Chanel?
Will you be posting an answer key for these things like eventually?
Yeah, I have the 3.9 answer key written. I just need to scan it.
Oh, okay.
And the multiple choice, I'm on like question 40 or something. I'm plucking away through it. Yeah, it's hard. I have a lot of distractions, and I'm trying to write, like I write the test at the same time as I'm kind of working through these. So if I find something, I'm like, oh, that's a good one. Let me write a variation of this. Or cook up something of my own that's like kind of along the same lines, but it's like, sounds like a different problem. So they don't go very fast because I'm not trying to race it. And then I'm looking them up at the same time on my end to make sure that I have the correct answer on the key and, that kind of stuff. All right. What do you guys want to do for the last 13 minutes here? Do you want to do another 3.9 question?
Yeah, can you do question 1?
Oh yeah, sure. Yes, of course. Yeah.
I don't know why I struggled with this one. This should have been much easier. You're gonna be so
Yeah, that happens. Okay. Just drop that in somewhere. It says a particle moves on the hyperbola xy equal to 18 for time t greater than or equal to 0 seconds. At a certain instant, y equals 6, dy dt is equal to 8. Which of the following is true about x at this instant?
Are you thinking the derivative both sides?
So yeah, I would start. Well, one thing I would do is I noticed that like when y is equal to 6,
Oh, x is 3?
x has to be 3. And then if I do the derivative, I get x dy dx plus y dx. Should be t, and that should equal 0.
Wait, why should it equal 0? Sorry.
Derivative of 18.
Oh, yeah.
Okay. So if I plug in then 3 times 8 plus 6 dx dt equals 0. So dx dt is going to equal 24 divided by 6. I should say negative 24 divided by 6.
Oh, yeah, because you're moving it.
So x is decreasing
I don't know why
4 units per second.
yeah, I think I way overthought it. I don't know, I think I was tired.
It's okay. We can ask about stuff. Not a big deal. But that's like if I was going to give you a related rates multiple choice question, that's about the level that I would give you. Something that's pretty direct. If it was a free response question, I would feel much more comfortable like making this much more detailed, because there I can judge the merits of your work and like figure out like why you got it wrong. If it's a multiple choice question, I want it to be pretty simple. Yeah. Where it's like you have almost everything you need, and it just like it's either all symbolic, like 2 I think is pretty fair as well.
Yeah.
And that's, 1, 2, some of these early one, most of the first half of this I thought was pretty direct.
Yeah.
And then it starts getting a little bit more complicated. The last 2 or 3 were pretty tough, and then the free response ones are usually pretty hard. Very common to see a complicated related rates problem in the free response section. Let's see. This is the first one. That's not bad. That's just like your standard cone related rate problem. We've done examples of that.
The last one.
Yeah, the lighthouse. Yeah, again, we did an example in the notes that was pretty similar to this. If we go back and look, where was that at?
It was, the last
Yeah,
one.
I think it's going to be pretty similar to this one, where you're going to end up with tan theta of x equals whatever. And then I would usually suggest always writing it as an inverse.
Okay.
That way you don't have to go back to the triangle and do any trig. But, that was pretty similar. And I have some more of these picked out that I just like, I was trying to get some of these problems picked out that felt doable, and like a couple of, like 1 or 2 pretty challenging ones, but most of them pretty doable. I just didn't want to give you like 20 of these things to do, because like you have enough to do. So I have some more of these too that I can include later on, or we can do some in real time on a different day. So on Friday, I'm going to try to do 4-3, which I think I can do in 40 minutes. And that's like, of these first 3 sections, this is like a big idea. This is a one that like kind of takes all these little pieces and puts it together. And this is stuff that frequently turns up on the AP exam in both free response and multiple choice style questions. But I think we can do that. And I wish I had more time that we could slow down a little bit right now, but I'm always kind of concerned about getting through everything we need to, so I don't want to stall too bad. If I'm a section or two behind at the semester, I don't feel too bad, but I don't want to be like lots of sections behind. You know what I mean? Because I'd still like some time at the end of the year where we can just like, here's a set of free response questions. We're going to work on these in class and then go over them next time, kind of thing, where we can do some like real practice. Is that okay?